and then we just find a pattern there. But now, notice something here. If we take the derivative of this one, y prime, we basically start from 1. Why do we do that? Why does it start from 1? Okay, I didn't show you all of this for nothing. Let's look at this one. This is the function. This is the series expansion of that. Notice something here. If you take the derivative of this one, c1 is the first term in that derivative. Let's look again. E to the x. If you take the derivative, c1 is the first term of that derivative. We did this a number of times. This one, the first derivative, c1, you just have that. So whenever you do that, that means that whenever you take the derivative, that means your first term will start at 1. So we're just going to take the derivative of the inside function, which is just cn multiplied by n x to the power of n minus 1. So that way, if you plug in 1, you have c1 multiplied by 1, which is c1. And if you plug in 1, 1 minus 1 is 0, x to the power of 0 to 1. Then you have c1 multiplied by 1 multiplied by 1, which is just c1, of it which you already saw of what's happening. The first term of the derivative should be c1. So if you had questions of why does it start at 1, this is why. Okay, so similarly, we know that the second to infinite, the second derivative of that will basically start at 2. Then we go to infinity, then we take the derivative of that one. So just end up with something like this, x to the power of n minus 2. So if we progress here, if we take the third derivative, we're just going to end up with something like this. If you take the nth derivative, just a similar process there. It doesn't really matter there. So you have cn, n minus 1, n minus 2, and you have x to the power of n minus 3. So if you take the number of derivatives, notice that what happens here. First derivative started 1, second derivative started 2, third derivative started 3, then you're just going to progress like that. So how do we actually apply this in order to solve our differential equations right here? Okay, so let's say maybe we have, let's start simple. Let's say we have y prime plus y equals to 0. We already know that the solution to this differential equation is that y equals c naught, or just some constant c multiplied by e to the power of minus x. Okay. Again, you can try this using separation of variables, and then you get the solution being c e to the power of minus x. Okay, but we want a solution in terms of like series. You want to use the series to solve that differential equation right here. Okay, this is the simplest example that you can ever approach in this thing, so bear with me on this one. So let's see. You're going to say y equals the summation starting at 0 to infinity of cn x to the power of n. Usually, like most of the time, they like using the term ordinary point. So it's basically x minus x naught to the power of n instead of just that. Okay, about the ordinary point, if we talk about the ordinary point, we're basically using this value. So this is a solution about an ordinary point, x equals 0, stuff like that. We can really, doesn't really matter. So if they give you an ordinary point, just know instead of x to the n, you're going to use this one. Okay, so now let's get back to our solution here. Y prime will basically be the summation starting at 1 to infinity of cn n x to the power of n minus 1. So we rewrite that differential equation in terms of our series there. So we basically have like the summation starting at 1 to infinity of cn n x to the power of n minus 1. And then plus the summation starting at 0, because it's y now, to infinity of cn x to the power of n equals 0. Now notice something here. This series starts at 1 and this one starts at 0. We want both series to start at the same point, but first, let's check what happens. If you plug in 1 here, you end up with x to the power of 1 minus 1, which is x to the power of 0. The first term contains x to the power of 0. And if you plug in 0 here, you also have the first term containing x to the power of 0. So they both start at the same x terms, so that's fine. We can skip that step. So if they don't start at the same x term, you have to make them start at the very same x term there. X to the power of 1 maybe, x to the power of 2 maybe. I'll do an example of how you do that in a moment. First, let's start and solve this one. They both started the very same x term here, so it's fine. We can skip that step. Okay, so now we want the both series to start at the same position. So you don't really need to think. Well, okay, you get what I mean. You just put k equals this term here for each series. So for the first series, k equals n minus 1. For the second series, you just have n here. So you're just going to take k equals n. Then you rewrite that series in terms of k. Plug in n equals 1 there. So you have 1 minus 1, which is 0. Infinity minus 1 is still infinity, so you don't really need to change that, because infinity is not a number, so it doesn't obey this kind of like operations. Okay, so then solve for n here, you get that n equals k plus 1 if you solve for n. So instead of c subscript n there, we'll just have c k plus 1, because that's n. And we have multiplied that with n, so we basically multiply with k plus 1, and then x to the power of k. Plus, plug in 0 here, you get 0. So we just have k equals 0. Plug infinity there, we have infinity. So that's it. And then you just have ck, because n equals k. And you have x to the power of k equals 0. These k's are the same. These k's are the same. So don't make a mistake and say they're different. Most of you are confused with that. Okay. So now you can regroup this, because these two series are in phase now. So we can basically just add the two together. But notice that when we add them, we can factor by x to the k. So you basically have x to the k there. On the first series, we remain with ck plus 1 multiplied by k plus 1. Okay, so now in the second series, you just end up with ck. So we have a plus sign in between, and then we just have ck. Remember, k goes from 0 to infinity there. So this is equals to 0. So the summation of an infinite number of terms gives us 0. So now we disregard x to the k, because x can basically be anything. So that means that we set this inside part to be equals to 0 for every k. So that means that ck plus 1 multiplied by k plus 1 plus ck equals 0. So if you rewrite that, you solve for the one with the upper k values. In this case, it's ck, and this one is ck plus 1. The upper one is just ck plus 1. Then this will basically be minus ck divided by k plus 1. And remember, don't forget to specify your k values here. K goes from 0. K is integer starting at 0. So k equals 0, 1, 2, 3, and it just progresses like that. So in this sense, now we want to express the k values instead. The k values, okay, how do I put this? We want to express this expansion in terms of just maybe C0 or C1. Sometimes you get sometimes you just get C0 and C1. So what we want is to express C, the coefficients in terms of the other one. Basically, the first coefficient, if we plug in 0 here, we have C0. That means we can express C1 in terms of C0, and we just work our way throughout that. Okay, so let's proceed. Okay, so yeah. Okay, let's start with k equals 0. If k equals 0, and we have k equals 1, we have k equals 2, we can have k equals 3, and we can progress like that. Let me use up until k to the 4th and see if we can get a pattern there. If k equals 0, plug in k0 here, you just get c1. This will be equals to k0 here, you say you have negative c0 over 1. So you just have negative c0 over 1. Okay, so plug in k1, here you have c2. If you plug in k1, you have c2. So this will be negative c1. So you have negative c1 over 1 plus 1. That will basically be 2. And now we have c1. We know that c1 is just negative c0 over 1. So this one just goes to c0 over 2. It goes to c0 over 2. Okay? Plug in k2, you have c3. K is 2, so you have negative c2 over 3. I mean c2 here. And this 2 is a subscript. Okay, so now c2 is equals to c0 over 2. So that means that we can have negative c2, plug in c0 over 2, then you just have c0 over 6, negative c0 over 6 there. And then c4 will be equals to, this is for k equals 3, right? For k equals 3. My things didn't align really well there. This one is for k0, this one is for k1, this one is for k2, this one is for k3. K3, we have negative c3 over 4 and C3 is this one. So we just end up with C0 over 24. 6 by 4 is 24. But I think we can basically see the pattern here. We can go on and try for K4. We have C5 equals negative C4 over 4. And then we just multiply 24 by 4. And we're just going to have 120 there. And then we have negative C0 over 120. So this means that the solution y equals, remember, our substitution here was that y equals c n x to the power of n. If you expand that summation, you basically just have c0 plus c1x plus c2x squared plus c3x cubed plus continuing like that. So c0, c1 is negative c0. So you have negative c0 x plus c2 is just c0 over 2 x squared plus c3 is just basically equals to c3 minus c0 over 6 minus c0 over 6 x cubed plus, you can progress like that. So you can factor by c0. So you have c0 and then you have 1 minus x plus a half x squared minus 1 over 6 x cubed plus progressing like that. So that's our series right there. If you cannot find what series is this, you can leave it here and avoid losing marks for incorrect answers. You can leave it here. But okay, let's continue. So you have C0. What's this expansion here? It's the summation starting at 0 to infinity of x to the n of minus 1 to the n over n factorial. I hope you can see that. I hope you can see that. Because if n is 0, you have 1, and everything just reduces to 1. If n equals 1, you have a negative 1 here, and you have an x there. So basically, this is just C0 multiplied by the summation starting at 0 to infinity of minus x to the n over n factorial. So this is basically, in fact, let's write it like this instead. C0 multiplied by the summation starting at 0 to infinity of 1 over n factorial multiplied by minus x to the n. And if you look here, we did something similar to that. We have the summation here. And if you look at these two, you have a negative x instead of x. So that means you'll replace this x with a negative x. So that means that the solution to that one will just basically be C0 multiplied by e to the power of minus x. And that will be the solution to that differential equation right there. Okay, so the series method of solving y prime plus y equals 0 works like that. Okay, thanks for watching. Don't forget to share and subscribe. And good luck.